Okay, so here's the thing. Dr. Moon did not just pull this out of his hat. He wasn't just like, oh, I wonder, platonic solids, that's a thing. He got some inspiration from this handsome gentleman. And this is Johannes Kepler, who was a 17th century astronomer, mathematician, astrologer, theologian. He made great contributions to music and harmonics, and is one of the most famous astronomers all time. Made huge contributions to our understanding of the cosmos. He was the first person to write an academic defense of the heliocentric universe, or heliocentric solar system, right? It's like still a debate about whether the Earth is the center or the sun is the center of the solar system. And Kepler got in there as the first one to write a defense, like, no, it's clearly the sun. Look at this data. So he had these he had the most accurate measurements of planetary orbits available in his day. And he's working with this guy. They never got along, but they sort of like recognized that they had to work together because they both had information the other needed. And so there's like this famous feud. They were never getting along. They're always mad at each other, but like, God, need that data. So they made it work. Now, in the year 1619, Kepler published a book called Harmonia Mundi, Harmonies of the World. And this is a seminal work in which he summarizes astronomical data that show how planetary orbits can be accurately modeled and predicted according to archetypal geometric structures. Guess which ones. And so this is his drawing of how the solar system is organized, and it should be looking familiar at this point. This is a set of nested platonic solids, nested spheres with platonic solids inscribed inside them. And let's talk about what that means. So here, let's start on the left with Mercury and Venus. Outer circle is Venus, the orbit of Venus. Inner circle is the orbit of Mercury. First caveat I'll say right away, planetary orbits are not circular. They are oblong. And this is the pulsative asymmetry of the cosmos, right? Life is messy. Space is not perfect. We're talking the realm of metaphysics. So the actual calculations don't quite line up. These are close enough measurements. So if we take the mean orbit of Venus, which is to circularize an oblong thing, then this works. And so that's important for me to say, just because there are people who say that this isn't true because it's not strictly mathematically precise. And I reject that, because wouldn't it be nice if a year on Earth were 360 days and there's a 360 degrees in a perfect circle, and oh, it'd be so satisfying, but it's not, because life is messy, creation is messy, there's pulsative asymmetries once time gets involved, and we're flying through space and it's just a little bit wonky. And so it's oblong, not a circle. But if we want to understand the underlying subtle superstructure of the whole thing, we can circularize and make perfect conceptually the imperfect observable thing. And then this math starts to click into place to like the 99th percentile. So, okay, that's the disclaimer. Orbit of Venus. And then you see the function, right? You draw those three circles, basically make a triangle inside that orbit of Venus, and you connect those dots and make a circle with those dots. Boom, that defines to within 99th degree of accuracy the orbit of Mercury. So there's this harmonic relationship between the orbit of Venus and Mercury. Now looking at Jupiter and Earth. using our familiar Star of David, which is actually a cube, right? That Star of David is the two-dimensional expression of a cube. That takes some visualization to work on it, but stare at a Star of David long enough one time and your brain will click into place. And so you see all this structure is like one Star of David, and then in the center of that one, another Star of David, and in the center of that one, another Star of David. And then you inscribe a circle on the inside of that third star, and that is just about perfectly the orbit of Earth around the sun. So again, this very beautiful harmonic relationship between the orbit of Earth and the orbit of Jupiter. And so this again is a 2D representation of the three-dimensional nested spheres, nested platonic solids that define these relationships. Let's see if we can get a better look at it. Oh, here's our spheres and cubes and octahedrons again. Okay, so this is the representation of the Earth-Jupiter proportion. May be created by spherically nesting 3 cubes or 3 octahedra or any threefold combination of them, right? So if you take that outer circle or that outer sphere on the left-hand side here, let's look at this one. That outer sphere represents the orbit of Jupiter. And then we do our simple process, cube, octahedron, cube, and then the sphere that fits perfectly inside that inner cube is the orbit of Earth. And sure enough, the same function works exactly the same, even if you start with an octahedron, right? So Jupiter out here, instead of a cube, start with an octahedron. Cube, octahedron, inscribe a sphere in the middle of that inner octahedron, and that's the orbit of Earth. Yes, Sam.
Just help me, because Jupiter doesn't revolve around Earth, so.
No, but they both orbit the sun.
Right.
So at the center point of all this is the sun.
Oh, the center is the sun.
The center is the sun, and the center sphere that's the Earth's orbit around the sun, right? So this is Jupiter's orbit, this is Earth's orbit, and somewhere in here is the sun. Got it? Cool. Good question. Okay, this is just yet another way of representing this, and so here, like we said before, the space between Mercury and Venus is actually 2 pentagons. It's 2 dodecahedron, right? So take outer circle is Venus, and then inscribe a pentagon. Inscribe a pentagon inside that, then draw a circle inside that pentagon. There you've got the orbit of Mercury. And that's this same relationship defines the relationship between Earth and Mars. Earth and Mars's orbit. And then 3 nested pentagons does Venus and Mars, and Ceres and Jupiter. So these are just some examples of the different spatial relationships that we can define this way. Yeah.
Sorry, maybe it's the gravitational field that makes it oblong, because like gravity bends space-time, so it might actually bend those lines longer, shorter.
Right.
Yeah.
Totally. You're onto it, and we're gonna talk about gravity in just a second.
Maybe it was perfect at one time.
Maybe it was perfect at one time.
It still is perfect. We just haven't accounted for gravity.
Yeah.
It's not unnatural.
Say more about perfect at one time. You're talking about the planet Maldek exploding and creating the asteroid belt.
That is not what I was
Okay.
saying. But this 99.4, 99.2, maybe it was closer to 100 at one point when the planets in the solar system was younger, and,
Right.
and was less affected by time and gravity and all that.
Yeah. Let's bookmark that, because I want to come back to that in the next part, because there's something juicy where we can explain the the slight messiness of it.